So going back to what we did before, this gear kind of collides with this. So if this happened in build, you'd be taking apart all this, which is a pain. So in Inventor, you can just fix this real quick. So you can like do like Control X and then Control V, and then let's just place it here. Yeah, so we're actually doing the opposite. No, we're going. Yeah, I was about to say that. So what everyone, we're like basically like, this might be a bit confusing, but so we're powering this gear. We're powering these gears. So we're doing small gear into bigger gear, which is torque, right? But we said earlier we wanted speed drive phase, so that might be confusing. Like Ian said, like we talked a bit about cartridges last time. So green cartridges spin at 200 RPM, but when you build this drivetrain, we're actually going to swap the internal gear in the motor to a blue cartridge, which is actually 600 RPM, which is actually like 3 times faster. So we can actually crunch out the RPM calculations right now for you guys. Um, okay. Yeah. Yeah, because like conventionally, like we just measured against the drive base we built last time, right? Like the standard Vex drive base, 200 RPM direct on 4-inch wheels. So yeah, so just like keep in mind in real life, this green bar would be blue because the internal gearing would be different. So we're just gonna constrain these onto the gears, just like before, like that. And then also like typically like on drives like this, like you want to use like 2 motors per side, which is like usually like the standard because one motor is too weak, especially like when your robot's like really heavy. I'm just trying to find the hole. Okay, this is really annoying. Mm-hmm. Because like if you have less power like going to your motors like whatever, like if the torque of your drivetrain is like too low, basically like it might struggle to move, right? So for example, you're pushing something, if the robot's not moving, all the electrical energy going into the motor is being converted into thermal energy, and that causes the motor to burn out, and you're gonna have a very bad time. So yeah. Yeah, if you guys have any questions, just put it in the chat and we'll be happy to answer. Okay, so this metal thing, by the way, is a shaft collar. Like we mentioned yesterday, it clamps onto the shaft to prevent it from slipping out. You don't see a shaft right now because I haven't put it in yet. So, yep. Okay, these are 4-inch wheels. We're going to put them right here, and we're not going to forget to use bearings. Okay, this side's good. We just need to do the other side. Okay, and we're almost done. So there's actually a little space between the bearing and the wheel, so we're just gonna put a spacer in there. So spacers are here. Typically there's two types. That we didn't go into this yesterday, but might as well talk about now. There's two types. There's a black one and there's a white one. So you see like there's like 0.500 OD and there's 0.375 OD. OD stands for outer diameter. Like the thicker the spacer, the stronger it is. And since this is a drivetrain, we typically like thick spacers because drive faces need to be strong. So yeah, and we choose about this size. Okay, so this is basically it. We just need to put in the shafts now. Is the wheel still hitting? No, it's good. Yeah, so basically what Jeffrey said, also like another hidden like benefit of bearing slots, if we actually look at the back, you can see there's like tiny teeth, right? And these actually like align with the square holes in the C channel to make sure there's like minimal play. So that's why I like to use it on here as well as spacers, because spacers, they don't have these sort of teeth that kind of align. So that's another added benefit. All right, it's time for shafts. I'm actually going to go into this library. Okay, these shafts might be a bit too short, but just a rough sketch right now. Okay, that's too much. Okay, so constraining shafts, just the same thing. You click the circle on it, and then the only difference is you need to apply offsets. So for this, you can just try values and eyeball it. And then finally this one. Inserts? No, not yet. Yeah, so Jeffrey is like kind of like for like talking about like joints. We'll look at joints like later, but yeah, joints are really important in fact. Just to like catch up, I don't know if Inventor's like frozen because it's frozen on my computer right now. But like what I just did was I mirrored this whole thing across the XY plane, so I don't have to like do all this constraints like all over again. And we'll just see how long this takes. Like mirroring's pretty expensive, so. Okay, is my computer gonna die? Oh my god. Yeah. Yeah, that's a really good point. So I've been doing something that's probably not good. Make sure you save periodically. Like make sure you save. Like I don't know how many CADs I've lost by not saving that like oh my I don't even want to talk about it. Alright, so okay, so you can see this mirrored on this side really nicely. I might as well take this and show you guys a cool sure is it still frozen? Okay, mine's fine now. Okay, that's strange. It's fine now. Okay, so as you can see, this thing mirrored it onto the other side. Obviously, we want to get rid of the C channel, but before, I might as well show you like some other constraints. So the first type of constraint is called a mate. So if we click flush, it basically makes two faces like aligned with each other on the same plane. So if you choose, okay, please let me select this. All right, it's not letting me select this. Okay, there we go. If you choose this face and then we choose this face, it basically makes them on the same plane. So that's pretty cool. Yeah, because what I'm doing right now is I'm going to put these things together. So I just deleted the cross brace and I'm gonna pop this side on. Yeah, so every insert constraint is analogous to putting a screw because it does the same thing. Alright, so basically this is what we did today. So we'll just run through it one more time, and I think it'll be nice to show you the full calculation so you can do like drive-based calculations yourself for game analysis. So, okay, to run through, these motors are running at 600 RPM, 600 rotations per minute. So it's going to be on a blue cartridge. These motors drive these 36 tooth gears, which in turn drive the big 84 tooth gears, which results in like gearing down. But since this is rotating so fast, it's still going to be faster than the normal 200 RPM drive phase. And we're going to show you why this is faster through math. And one more thing to note that I don't think we noted before is the wheels are linked by gears, right? So if I try to rotate this wheel in real life, this wheel will also be rotating because it's linked with gears. This is a really good thing. Yeah, odd number of gears. So like this is really nice because we typically want to link the wheels in some way, shape, or form with chain or whatever, because like as we mentioned like last time, like we want power to be distributed evenly across the chassis. So let's just say like if our chassis was like being like rammed and it was like, oh shoot, but it was like tilted upwards, but obviously not this much, but it was tilted upwards a little bit. Oh my god, it's so annoying. But okay, like this, it was tilted upwards like this a little bit, and yeah, then these wheels won't be touching the ground. And if this was direct drive, it only has 2 motors of power on the back wheel. But since this is all linked, you effectively have 4 motors of power on the 2 back wheels. So this is really nice. Okay, so I'm gonna save this and upload it soon. But okay, now we might as well show you the calculations. So let me share this tab. Okay. Okay, so as we said, the motor was running at 600 RPM, so we can just write 600 in here. 600 is rotations per minute. So, okay, so now, can I get a scribble pad? Wait, is there anything I could write on? Or should I just do Paint? Okay, let's just use Microsoft Paint. Right, that's it. Okay, so basically our motor was running at 600 RPM. And then 600 rotations per minute. And then we're running on 4-inch wheels, right? So the wheels are 4-inch in diameter. So if we calculate the circumference of this, it's going to be equal to 4 pi inches, right? Okay, so we know the circumference is 4 pi inches. We can do this. So 600 rotations per minute times 1 rotation. 1 rotation of the wheel is 4 pi inches. Okay, and then so if we do this rotation like that, wait, we're trying to find 257. Oh wait, I'm just doing, okay, wait, okay. Oh, calculate the actual speed. Okay, JK. So, okay, so we're calculating the gear ratio, right? So discard this. This is something else. Okay, so we have our gear train was something like this, right? Three 36 tooth gears to two big 84 tooths. So the ratio of 36 tooth, which is going to be 36 tooth to 84 tooth, is going to give us our RPM. And this is again relative to the drive face we built on the first day. So if we actually crunch this out, if we do 600 RPM times 36 divided by 84, that's going to give us 257.142, whatever. So this chassis is 257 RPM equivalent on a 4-inch direct drive tank drive. So yeah, this is where this number came from. And this is fast. So if you want a fast drive face, you want to find something around this value. Some teams go up to 280, depending on the game, and some really monkey teams, cough cough 231Z, go all the way up to 333 RPM or whatever that they want. This is like... Yeah, so it really depends on like preference. Like for some drivers, this is too fast, but yeah, we trust you can make your own educated decisions based on your testing. But again, testing, like of course, like test everything you build, and it should be good. So yeah, let me just close this. Okay, so this is basically all I had to say. So I think we can call it here. So does anyone have any questions or anything?